Hey y'all, so for this video we're going to look at section 6.2, but before we do that, let me show you what to do for attendance today. So today, Wednesday, tomorrow, Thursday, and Friday this week, you're going to do your attendance differently. You have to do your attendance through this form. Me and the other teachers will be in a bunch of trainings, so we're not going to be able to do attendance. So you have to do it this way. You're going to do this the same way for all of your classes. So for each class, you should see a link. Your teacher will provide that. It's the same form for each class. Click that, and it's a really quick thing. You got to put your ID number in there, whatever it is. Say, yes, I have done work today for my first period, or second, or third, or fourth. And then make sure to date it as well. So you're going to do this the same way on Wednesday, Thursday, and Friday. All right. So that's taken care of. Again, this is right on the front of AP Stat 2. You can't miss it. Big link in the front. All right, so once you've got your attendance taken care of, we can take a look at some statistics. All right, y'all. So this week's weird. We know that. So for Wednesday, Thursday, and Friday, you're going to have a couple assignments to get done. This video is going to be posted. There'll be another video following up, and then there'll be some homework to work through. And I'll make the homework Friday, so you can kind of parse out your time however you want. Again, it's all flexible, but you must do your attendance every day. Wednesday, Thursday, and Friday, doing your attendance like I just showed you. Okay, so this section is all about transforming and combining random variables. We have seen transformations on variables already. We saw this back in some other chapter. Hopefully, the big picture here seems pretty familiar. All right, so we're going to learn through a couple examples. Let's say we have this probability distribution here. El Dorado Community College considers a student to be full-time if he or she is taking between 12 or 18 hours. The number of hours x, so there's our random variable, x, capital X is our random variable, which represents the number of hours that a student is taking at this college. All right, and then we have the following distribution. So 25% of students are taking 12 hours. Let's stop that before it gets really annoying. Yep, it's already annoying. 25% of our students are taking 12 hours, 10% are taking 13, 5% are taking 14, 15% are taking 30, and so on. So we always want to take a look at our data before we do any calculations. So what's kind of interesting to me is that we have these kind of big spikes at 12, 15, and 18. If we were to graph this, we're not going to graph it, but if we were to do a histogram or something like that, we would see sort of trimodal data. We have these sort of three big humps, and that makes sense. If you've ever tried to enroll into, or when you do eventually enroll in college classes, most college classes are 3 units per class. So it makes sense that we'd have multiples of 3, which are the most popular credits. But then you have some off classes, which are only an hour, like an extra lab on a class, or it's not so important. But it's always interesting to look at our data and ask questions about why. Okay, so for this it says to calculate and interpret the mean and standard deviation. So first we can do the mean of x. So the mean of a random variable goes by another name as well, called the expected value. We call that E of x. These mean the same thing. You can use these notations interchangeably, but you should recognize both. So I'm just going to do mu. So mu of x. And on my formula chart, there is an equation for this, but I'm going to go ahead and use my calculator to solve this. So I'm going to enter the data into the list. Okie dokie. So I've got my data in the calculator, right? Outcome values in list 1, probabilities in list 2. So now we're going to go over to our PAL 1var stats, right? Even though we're working with more complicated random variables, we still want really basic 1 variable statistics, the mean and the standard deviation. So my 1var stats, L1 is going to be my list, L2 is going to be my frequency list, right? Probabilities, or how frequently each of these things occur. All right, and we get our mean. So we get 14.65. Now, if I'm taking the AP test, it seems kind of lame to just write this out with no explicit explanation of how I got those values. So you can maybe describe what you've done in the calculator, or what I like to do here is to just kind of jot down that formula. So I can say, okay, I know the formula, and if I don't, I can just look at the formula chart. It's the sum of each x value, so we call that xi, times the probability of each x value. So just copying down that formula chart from the formula chart turns this into a level 5 answer, a really nice answer. Okay, we don't necessarily need to show the work actually doing that. We can use the calculator, but we should have some sort of explanation of where that comes from. Again, to break down the notation here, x to the ith, or sorry, xith. So this is x1, x2, x3, and so on. So we're adding up every x is what that's saying. We iterate through the x's. And then we multiply times the probability of each. Okay, for the standard deviation, we can do something similar. We can just jot down the formula. Again, just grabbing this from the formula chart. We take each individual x value and we subtract the mean of our random variable x. We square that deviation and multiply by the probability of each one happening. Again, these formulas are on your formula chart, and even though I'm not going to use this formula, I'm going to use the calculator. It's nice to write it down. If this were an AP style question and this is my open response, I want to explain where I'm getting these numbers. Cool, we already got that number over here. Standard deviation is 2.056. Okay, so I've got my answers. I use the calculator to find those. Next, I want to take a second to interpret that. So the mean is 14.65 hours. So we know that a student can't take that many hours. They can take 14 or 15. They can't take some fraction of hours, probably. Well, definitely, we know the possible outcomes. We'd say something like this. That value doesn't describe anything that can happen if we look at one random student, but if we randomly select many students, then the average number of hours taken will be about 14 point whatever. Okay, so this is how we interpret the expected value. Okay, how do we interpret the standard deviation? So standard deviation, again, describes the variance of our data. Nerds. So we could say, to describe this variance, or sorry, this standard deviation, we would say the number of hours typically varies from the mean by about 2.056 hours. Now, we aren't spending enough time really in making sure to interpret our answers. That's a really important part of statistics. Not knowing just how to find the answer, knowing how to talk about it is really important. So if we're finding an expected value, we're finding what to expect if we take a bunch of random students from this distribution. If we select a bunch of students, on average, they'll take about 14.65 hours. Also, if we select a bunch of students at random, the number of hours is typically going to be off from the center, from the mean, by about 2 hours. All right, so if we take a student, we can expect them to be, on average, off by about 2.056 hours. Okie dokie. So that was sort of review from the first video. Now let's look at actually making a transformation. So, oops. Section says at the community college, the tuition for a full-time student is $50 per unit. It's a cheap school. So if T is going to represent the tuition charge of a randomly selected student, t equals 50x. So we have two random variables now. T is the random variable representing amount of tuition they're going to pay, and x is a random variable representing how many hours they took from this last problem. So the tuition is $50 times the number of hours. So we can get a new random variable by taking an old random variable and transforming it, by multiplying it in this case. So let's see what we get. We get a 12-hour person is going to pay $600. That makes sense. 12 times 5, 50. 12 times 50 is 600. All right, and we have the same probabilities as before. All right, we still have 0.25, 0.10, 0.05, and so on, because it's the same thing here. Okay, so now we're going to do our same calculations again. So this time we're finding the mean of t and the standard deviation of t. All right, so let's go back to our lists, and I'm just going to edit list 1 to represent these new numbers. Okay, so we've got our new data in there, and once again we're going to do one var stats. L1 again is our random variable t, the possible outcomes of that, and L2 are the probabilities of each of those possible outcomes. Oops. Okay, so we get a mean of 732.5. Earlier I said it's good to show some kind of work here, even though we're using the calculator. Another way to do this would be to start calculating it by hand to show that you know how to do it if you wanted to, but then not actually do it. All right, so get some brownie points showing that you know what to do. We take each outcome, multiply by its probability, and do that all the way down the line. And then you just do a little dot, dot, dot there, saying like, I could do it if I wanted, but I don't want to. We get 732.5, and we're talking about tuition here, so that's $732.5. Since we're in dollars, I'll go ahead and throw second decimal place there. All right, we can do the same thing for standard deviation, although this is a little bit uglier to describe the first few terms. Cool, so really great way to show your work here is to start doing the math and then give us a dot, dot, dot. And again, you can do this. You can also copy down the formula from the formula chart. Either one of these is a really nice answer. It shows you know what you're doing, even if you're just using the calculator. And getting the answer is the most important part, of course, but you want to show your work so that anyone who comes along could replicate it. Here, this time, we're going to do a slightly different transformation. So notice what happened when we transform this variable. So we have our original mean was 14.65. Our new mean is 732.5. You may notice here the relationship between these. We multiplied each individual value by 50, and so the mean got multiplied by 50. All right, pretty simple to see how the mean was changed when we made that transformation. Same goes for our standard deviation. 2 point something times 50 is 100 point something. Right? We can see that connection. We just take the mean and standard deviation by multiplying by 50. So instead of re-entering all the data, we could have just taken the values we had already found and multiplied by 50. Whoops. All right. Let's take a look at this one. So this time we are taking, we're taking that total tuition cost, and then on top of paying $50 per credit, they also have to pay $100 per semester in fees. So they're not really, the average student's not really going to pay $732. They're going to pay that $732 plus an extra $100 for fees. So we have this new final distribution here where our overall cost, you can see, is just $100 more than the tuition cost. So from 600 to 700 and so on. All right, again, we want to find the mean of this new random variable, which we're calling C for overall cost, and the standard deviation of that overall cost. Cool, so maybe flashback to what we talked about when we did this the first time. We talked about transforming variables. What's your prediction? So our tuition mean was 732. and we're adding $100 to every one of these values. So what do you think the new mean is going to be? And make that same prediction for standard deviation. We were at a standard deviation of 108.2. If we add $100 to every value, how would our standard deviation change? Think on that for a second while I update my data. So this is now 700. And we'll run one var stats one last time here with our last data. All right, so if you guess that our mean would go up by $100, since we're just adding $100 to each value, then you're correct. Okay, if we add $100 to every value, every outcome of our random variable, then the average is just going to go up by 100. Now, if you thought the standard deviation was going to go up by 100, then you're wrong. You didn't remember that adding or subtracting to a distribution does not affect the spread. Right, if you think about this sort of algebraically, let's say we have some distribution here. Our example here is not normal, but let's say we had some example distribution and we added $100 to it. So it's going to be the same distribution just over here. And again, this data is not normal, but just an example. All this is going to do is just slide the distribution to the right or to the left if we're subtracting a value. So the same distribution is there, the same spread is there, but yeah, so our center is different, right? You can see the average has gone up, but the actual shape and spread are the same. Okay, so real quick, let's summarize what we just saw. So we know what a random variable is at this point. It's a variable that takes on values determined by some chance process, like choosing a random student or rolling a die. Expected value is the mean of a random variable. We can see that to calculate that, we take each outcome and multiply times the probability, and we add that up for all possible outcomes. You can find that again on your formula chart. And we just saw that if we multiply or divide by some constant, so we take all of our hours and we multiply times 50, then the mean and the standard deviation are going to be multiplied as well. Okay, so you saw the mean went up by times 50 and the standard deviation went up by times 50. So the shape stays ultimately the same, right? You're going to have the same shape. If it was symmetric before, it's still symmetric. But the center and the spread are going to be multiplied, right? Our center is going to go up, it's going to get multiplied, and the spread is going to be multiplied as well. And then we saw something slightly different when we added a value. So we added $100 to each outcome, and we saw that the mean increased, but the standard deviation stayed the same. All right, we just slid that distribution over, so the shape and the spread were maintained. Nothing changed there, but the center was slid to the right in this situation. Okay, now let's look at combining random variables. What if I wanted to take two random variables and put them together? Okay, that's possible, and it's actually pretty intuitive. So for the average, it's going to be really straightforward. The average of some totaled random variable. So we have, I guess this needs a little explanation. We have the random variable t, which is a combination of random variables x and y. So we added x plus y to get the new random variable t. The average of this new random variable t is just the sum of x and y. It's really simple. So whichever way we if we add our random variables, we just add the means of each individual random variable. And we'll look at an example in a second to really cement these rules in the old noggin. For standard deviation, we can't do the same thing. We can't just add standard deviations together. We need to do a Pythagorean sum. So what we're really doing here is we're adding the variances. So the variance is the standard deviation squared. Cool, so we can pretty simply get the new standard deviation, but you just have to remember, we don't just add them together, we do a Pythagorean sum, right? You might remember a squared plus b squared is c squared. This looks really similar. Okay, so why would we need to do this? Why would we need to combine random variables? Let's look at an example. All right, suppose we have a certain variety of apples, and the weights of these apples has been proven to be approximately normal. And the mean is 9 ounces, and the standard deviation is 1.5 ounces. So this is our distribution of an apple, right? If we took a randomly selected apple, this is what the distribution would look like. But what if we wanted to take 12 apples? So we're going to call this distribution over here X. So X represents the weight of a randomly selected apple. Okay, and then we're going to have T is going to represent the weight of 12 randomly selected apples, a bag. Okay, so we already know the distribution of X, right? And this is not a discrete distribution like we saw in the previous problem, where we had a limited number of possible outcomes and then their probabilities. Here we have a infinite number of possible outcomes. The apple could weigh 9 ounces. The apple could weigh 9.5 ounces. The apple could weigh 9.25 ounces or 9.251 ounces. There's an infinite number, depending on how we're measuring this, there's essentially an infinite number of weights that the apple can take. And each of those has an associated probability, which is represented by the height of our normal distribution. Okay, so now we want to take this distribution and transform it into T. So essentially what we're doing is we're going to take 12 of these random variables X and put them together. So T is equal to X, the first one, we'll just put a little label there so we can keep track, plus the second one, plus the blah, 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 blah one, up to the 12th one. So you can see T, the weight of 12 randomly selected apples, is going to be the total, the sum, of just adding up 12 X variables. Okay, so what if we wanted to find the mean of T? Well, we just saw that if I want to find the mean of a combination of random variables, I can just combine the means. So the mean of this can be the mean of X, the first one, plus the mean of X, the second one, plus the blah, 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 the mean of X, the 12th one. We can just add up all those means. So if the mean was 9, they told us that in the problem, we just need to add up 12 of those. Or, to do it quickly, multiply 9 times 12. Okay, so the average weight of a bag of 12 apples is going to be 108 ounces. Okay, so we're already starting to think about our new distribution. I'm going to do that in a different color over here. Distribution of T. And actually, if I wanted to keep it somewhat consistent with that other drawing, it would be more spread. We're going to see a bigger standard deviation. Okay, the average weight of a bag of apples we just found was 108 ounces. Okay, but what about the standard deviation? Let's go back to our math here. The standard deviation of T, I can't just add these together. I can't just look at the standard deviation of x1 plus the standard deviation of x2, the blah, 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 standard deviation of x12. That doesn't work, okay? These are not equal. But we can actually do this pretty simply. Instead of adding the standard deviations together, we can add the variances. A variance is just the squared standard deviation. Okay, so we can actually calculate this by adding these all together. So let's see what we got. The standard deviation of a single apple is 1.5 squared. It's 1.5, and then we're going to square it. Okay, so it looks like we need to square 1.5 and then add whatever that is to itself 12 times. Okay, so 1.5 squared, 2.25, and then we need 12 of those, right? We got 2.25 added together 12 times. So in other words, we can just multiply. Okay, so we get the standard deviation of t squared is 27. We don't want the standard deviation squared, we just want the standard deviation. So I'm going to take a quick square root of that. And the square root of 27 will be a little bit over 5. We get 5.196 ounces. Okay, so we now know the distribution of a whole bag of apples. So again, what we did here is we wanted to know if a single apple has a distribution of this normal distribution with a mean of 9, a standard deviation of 1.5. We can use that information to find the distribution of a whole bag of apples, which would be 12 of these randomly selected apples. So again, to get this distribution, we add 12 versions of this random variable x. So to find the mean, we just simply add the mean over 9 times. So we found that pretty quick. And then for standard deviation, we have to think a little bit harder. We have to square each one and then sort of do this Pythagorean sum instead. So just remember, if you're trying to find the standard deviation of combined variables, you have to square them first. Okay, so now we can actually answer the problem. We haven't done that yet. We've done a lot of work, but we're not there yet. What's the probability that the sum of 12 apples is less than 100 ounces? Maybe our bag of apples says 100 ounces guaranteed or something. We got to know what's the probability that we're lying to people. Okay, so looking at our distribution, we have a standard deviation of about 5.196. So the first standard deviation is going to be right in this area. Okay, so I'm just kind of eyeballing what we're looking at here. So that's about 103. Okay, that distance, if I go down another 5-ish, we're at like 98-ish. Again, I'm just kind of eyeballing this so I can get a good sketch. So we're looking at what is the probability that we're less than 100. This doesn't need to be a perfect drawing. I'm just using this as a tool to help me understand if my answer is going to make sense or not. Okay, so we've done problems like this a lot. Hopefully you feel pretty comfortable at this point working with our normal distribution. So what's the probability that t, right, this new variable, not x, but t, is going to be less than 100? They just said less than. I'm going to take that off, even though it doesn't really matter for a continuous distribution. Okay, well, to calculate this, I'm going to use my calculator. I'm going to do normal CDF. Okay, so we got everything thrown in. We're ready to calculate. We got 0. Let me double check that I did this correctly. Nope. You'd see I made a mistake. And I didn't see that mistake before I hit calculate. Maybe you did. Maybe you saw how dumb I was being. But this is super common, right? It's easy, especially with these physical calculators or using this version, it's easy to make a mistake. But I looked at this and I thought, I know my probability is going to be low, but I didn't think it was going to be so low that my calculator would just say it's 0. So I went back and checked and I found that mistake. So good lesson learned here. If you make a drawing, if you sketch it out first, that'll really help understand if your answer makes sense. I'm just going to say I did that on purpose as a teaching method. Okay, so there's about a 6% chance that your bag of apples is going to be less than the guaranteed 100 ounces. Okay, so that was a little bit lengthy for a video again, but our goal here is to understand how to work with random variables. They're a really important part of statistics. We need to know how to transform them. Often we take a random variable and we add some amount, we multiply some amount. Or maybe we need to combine multiple random variables, like in our apple example. We need to know how to work with these and what the rules are. So we did that today. So for 6.2, you're going to have a couple homework problems so you can practice this, and then we'll head right into 6.3. All right, thanks you guys. Take a look at the homework that's been posted, and good luck.